Okay, so good morning, everybody. Welcome to one more relativistic physics class. Let's see. So today will be lecture 11. Okay. So let's just recapitulate what we have talked about, okay, in the past couple of lectures. In lecture 8, I talked about some identities involving additions of gamma matrices, additions of velocities and gamma matrices. And then I gave you a general prescription for writing down the perpendicular and parallel components of a velocity vector under velocity addition. And then showed you that there is a nice expression which can be obtained for the gamma factor of the relative free velocity using the fact that the inner product of two vectors is invariant under different frames of reference. Then gave you a very quick derivation of the velocity addition itself, which is actually quite straightforward. Then in lecture 9, well, what was lecture 9? I think lecture 9 was all problems, right? And then lecture 10, the last class we had, we talked about the four velocity vector. Well, we had talked about the four velocity previously. So this time we talked about the four acceleration, and the fact that the four acceleration is always orthogonal to the four velocity. And also I pointed out the fact that, well, these objects, we call them vectors, but they are not really vectors in the traditional sense. They are not, I think the way to say it would be that they are not elements of an affine vector space. So you cannot add two such vectors to get a third vector, which is also has the same properties. Okay. So for instance, if you take two velocity vectors and you add them, then you can easily show that the resulting object does not have unit norm. Unit meaning -1 in this case. So if it does not have a unit norm, then it cannot be a velocity vector. And I started talking about the momentum 4 vector. And again, the same caveat applies to this, that you can't just take the momentum 4 vectors for two different particles and add them together to get the momentum 4 vector of the total of the combined system. Now this momentum 4 vector, it's actually the energy momentum 4 vector, because the time-like component is the energy divided by c, and the space-like component is the spatial momentum. And if you take the norm of this vector, you get the rest energy of the particle divided by c square. Okay. So we have p mu equal to minus E naught by c square. Okay. And this is always less than or equal to 1, right? Which means that p mu is a time-like vector. And it has to be, because if it describes if it's the four momentum of a massive particle, then it has to be a time-like vector, right? Because a massive particle can never move outside the light cone, right? So if this is the light cone, then a massive particle can only move such that its tangent vector is always lies within the light cone, right? Its velocity 4 vector can never lie outside the light cone. But what if the rest mass of the particle is 0? So you have a massless particle, right? And what sort of objects are described by massless particles? Anybody?
Photons.
Right. Any others?
Massless neutrinos.
Yes, true. Neutrinos. In the massless limit. And anything else? Gravitons. Okay. So basically any massless. Right. So for such things, for such objects, what happens to the energy momentum vector? It is 0. So it's null. So which makes sense because this means, right? So this implies that you will have the relationship E is equal to PC, where this P is the length of the free momentum. Now let's talk about the behavior of this vector under Lorentz transformation. Let's see what happens. So let me write down the components again. Okay. And so what will we get? We will get P mu prime is equal to lambda mu prime mu, P mu, right? Under some Lorentz transformation given by this matrix lambda. And let's take this matrix to correspond to, again, our usual boost in the x direction, boost along the x axis, right? So boost means change of velocity, right? So what happens if you write P mu as E by C, comma Px, Py, Pz, then under this transformation, these components, right, they will only affect the Px and Py components. These two will remain unchanged. So P mu prime will be, let's say, E prime by C, Px prime, and then Py, comma Pz. These will remain unchanged. And so what is the relation between these? So E by C, comma Px prime, so gamma minus beta gamma minus beta gamma gamma, E by C, P. Okay. So we get E prime by C is equal to gamma E by C minus beta Px, and Px prime is equal to gamma to minus beta E by C plus Px. Right? So I'm just taking this matrix and multiplying it out. That's all I'm doing. Now, let's say that in the initial frame of reference, the particle had a 3 momentum such that its angle with respect to the x-axis was theta. So what would be this angle theta? Well, this would be the x component of the momentum, and this is the perpendicular component of the momentum. So the perpendicular component is what? It's root of py square plus pz square, right? So we would say that tan theta, the apparent angle of the direction of travel of the object would be given by this expression p perpendicular by px. In Steen says py is equal to p perpendicular. So, but I mean, if you want to be like more correct about it, you have two components. So you should refer to, you should not neglect both of them. 1 second, please. Okay, just 1 second. Okay. All right. So now we can ask the same question about the angle of travel in the O prime frame, right? With respect to whom O has been boosted in the x direction. So here what will happen is you'll get P prime, then P perpendicular, and remember P perpendicular prime is equal to P perpendicular, it doesn't change, right? And you'll get Px prime. So tan theta prime will be P perpendicular by Px prime. Okay. Let me write Py prime or Px prime. This is equal to P perpendicular divided by Px prime. Now Px prime, what is Px prime? Is this expression. So let me just copy that and paste that over here. Right? Okay. So now I want to express this tan theta in terms of the angle in the initial frame of reference. So I want to express it in terms of these quantities. I want to write tan theta prime in terms of tan theta. So tan theta, just to remind myself, is this over px, right? Now, so how do we do that? Well, one thing that you can see is that we can just divide both sides of this expression by px, the numerator and denominator, not both sides. And you will get that tan theta prime is equal to P perpendicular by Px over gamma into minus beta E by C times Px plus 1. All right. So now in this expression, what do you get? You get in the denominator, you have gamma, and then you have this expression beta E C Px. Okay. Now what is this quantity? So beta is V by C. So this becomes V by C square. Okay. And now what is the relationship between, how do we write this E? Well, we can right. So how do we write this? Well, it's very simple. This, we take this momentum to correspond to a beam of light. So if it's a beam of light, then we know that the momentum for vector will be null, right? And if it's null, then you get that E is equal to PC. Okay. So I can write this expression as E is equal to PC divided by PX. Okay. That's right. I think that's right. Yeah. So I get tan theta prime is equal to tan theta over gamma. Now in this expression, what do you get? You get, so first of all, this factor of C cancels out. C cancels out over here. And did I do that right? I think, I hope so. And you get minus V by C. Now what is this quantity? P length of vector P divided by Px. So you can see what this quantity is. It is this, the base divided by the length of the vector, right? So I can, so maybe it's better to write like this: Px by P is equal to cosine theta. Okay. Right. And now we have to be careful about one thing, which I've not been careful about, is that this boost, right? This boost, it corresponds to some velocity V, right? What is this velocity V? It's the velocity of the O frame as seen by the O prime frame, right? So that's what this is. This is gamma V. But what is this E? E is the energy of the photon. And which photon is it? It's this guy. So if I write down this expression here, this is not V. It cannot be V, right? Okay.
So that V comes from beta, so it should be same as that in gamma, right?
Oh, you're right. You're right. Yeah. Sorry about that. Yeah. Okay. So I think I have to use a different relationship. Let me just derive that relationship quickly. Steen mentions it, and you don't need a null particle. So yeah, sorry, you don't need a null ray for this. So what is that relationship? We get this energy momentum is equal to E by C comma P, and right, and then E is equal to gamma m naught C square. P is equal to gamma m naught. I'll write it as U, okay, to distinguish it from this V. So if you take this momentum P and divide it by E, what will you get? You'll get gamma m naught u magnitude over gamma m naught c square. So you get gamma m naught, you get u by c square. Right, so this is true for any object, not just for a massless one. So I want to use this expression here, and right, so now I can write this expression beta e by c px. It becomes v by c square, and then e can be written as, using this relationship, e can be written as vector magnitude p c square over u, and then divided by px. Got it. So c square cancels out, right? And now I have v, velocity v, divided by velocity u, and p by px. Okay, p by px. Yeah. And what is this p by px? P by px is equal to 1 by cosine theta. So I can write that as v by u cosine theta. So putting all of this back in this expression, what do I get? I get tan theta prime is equal to tan theta on top divided by gamma v times minus v by u cosine theta plus 1. Now you just multiply through, you will see that the cosine theta factor will cancel on the top and bottom, and you'll get sine theta gamma v times u cosine theta minus v. Right. So this is the expression relating the angle, apparent angle of propagation of a particle in the moving frame with that of the apparent angle of propagation in the rest frame, and well, in a different frame. And here, what is v? V is the boost velocity, and u is the particle velocity, well, the particle speed, I should say, in the O frame. Okay. Now he gives a graphical interpretation of this result, but I'm not going to go to that. What I can do is talk about what happens when what happens for a null particle, right? So for a null particle, what will happen is, for a light-like particle, the particle speed in the theta frame for a massless particle, this u will be equal to c. Right?
So won't there be a u in numerator also? U sine theta by gamma v.
Oh, did I miss that? Thank you. Yeah. All right. Okay. So for a massless particle, u is equal to c, and then I would get tan theta prime is equal to sine theta O gamma v into c times cosine theta, and again, yeah, c times sine theta minus v. And it's easier to write this in a slightly different form using the fact that I can express cosine theta prime the cosine of this angle in terms of this thing, px prime divided by p prime. But now for a massless particle, I know that E is equal to Pc and E prime is equal to P prime C. So I can write cosine theta prime is equal to Px prime divided by E. So let me write that down. Px prime over P prime, which is equal to Px prime over E prime by C times Px prime by E prime. And now I can just use the Lorentz transformation equations to substitute in this. So what are the Lorentz transformation equations? They tell me that Px prime is this quantity and E by C prime is this quantity. So I can copy here, paste it in the, for Px prime, and then for E prime by C, I get this thing in the numerator. Comma cancels out, right? And again, what I do is I divide both sides by Px. I divide both sides by E by C. So what will I get? Cosine theta prime is equal to minus beta plus I'll get Px divided by E by C. What is that? That is cosine theta divided by 1 minus beta cosine theta. So this is, and this I will just write as cosine theta minus beta. So this is the relationship between the apparent angles of a propagating beam of light. Okay. All right. So this leads to all sorts of interesting optical effects, which we will talk about in one of the later classes. Okay. One is called the headlight effect. And I guess for the headlight effect one, you don't really need. Right. So yeah, I can talk about the headlight effect right now, in fact. So what is this headlight effect? Okay. Now, so let's say that you have some frame of reference. You have some other observer, O prime. With respect to O prime, O is moving boosted with some velocity V, right? So what does this angle, what is the apparent angle of this beam of light, right? As seen by O prime, right? And we can take this particle or this whatever this light source is, we can take it to be at rest in the O prime frame of reference. And so we get, using this result, right? We see that, well, this is the result. Now, from this expression, what can we tell about about the apparent angle? Well, the apparent angle is going to reduce. So if this is the what the light looks like in the rest frame of the object, in the moving frame, what will happen is that this will become theta prime and theta prime. So now this has another consequence, that let's say that this object is at rest and it's emitting light in all directions. So it's just an ordinary bulb. So we can take two of those light beams, one light beam that goes in this direction, one light beam that goes in this direction. There are other light beams also going in all the different directions, but we'll just take these two. Now, what does this correspond to? This corresponds to theta is equal to pi by 2 here, right? And now I look at this same thing. I set this in motion, right? So I boost this whole light source. And when I boost this light source, what do I perceive? Well, according to this picture, what will happen is, so this guy is now, it's moving, it's a moving light source. And now these light rays are bent inwards at some angle, theta prime, like this, right? So as your particle becomes more and more relativistic, what happens? The light that is emitted by the particle appears to be focused more and more narrowly in the direction of motion, right? So now it is not the case that there is no light emitted in the other directions. Light is still being emitted here and here, okay? So, but most of the light is concentrated in this forward direction. So it looks as if, like when you have a highly relativistic particle that is moving towards you, and if it's emitting some radiation, let's say, it appears that all the radiation is being emitted in this direction of motion. So it looks like a headlight, as seen by some observer here. All right. And then we will talk more about the distribution of the power that is emitted as a function of angle. We'll talk more about that in a later class. Okay. All right. So now I'll come to the next topic, which is force. We'll talk about relativistic forces. So again, now let's see, we have the 4 vector, position 4 vector, we have the velocity 4 vector, which is dx mu by d tau. We have the momentum 4 vector, which is m naught v mu, right? So what should be the force 4 vector? Well, the force 4 vector will just be this d, the momentum 4 vector divided by d tau, right? So what is this? This is d by d tau of the momentum 4 vector is e by c, comma p. So this becomes 1 by c dE by d tau, comma dP by d. Okay. So let me take this quantity. This is the force 4 vector. And again, what is the relationship between d tau and dt? What is d tau? D tau is the time as measured in the rest frame of the moving particle, and dt is the time as measured in the rest frame of the observer who is looking at the moving particle. So we can write this as using this expression gamma. And what is gamma? Gamma, we have to again be careful. Which gamma is this? This is the gamma of the boost, not the gamma of the particle. So I'll write gamma V, then dE by dt, and a factor of 1 by c is also there. Let me put that 1 by c dE by dt, and dP by dt. Okay. Now in this expression, you have two quantities. One is dE by dt, one is dP by dt. Now, what is the interpretation of dE by dt? Right? It's a rate of change of energy of the particle as a function of time. Right? Now, what is the meaning of the rate of change of energy of anything? You have some system S, and I say that the energy of the system is changing at this rate. How should I interpret this? Well, this can be interpreted as the rate at which work is done on the system, right? So if you do some work on the system, what will happen? The energy of the particle of the system will change, right? So you have this relationship. Well, if you're talking about a thermodynamic system, then you will also get a TDS term, but we won't worry about this for the time being. Set this to 0. Right? So we can write this quantity as gamma V, the rate at which work is done. So it's like the power. And what is dP by dt? dP by dt is just the normal definition, the Newtonian definition of the force on the particle. So the force 4 vector can be written as gamma V W by C and gamma V times which is the Newtonian force. Okay. All right. Now, this is the force 4 vector. Then we have one more 4 vector, which is called the wave vector. Okay. So after in later classes, we will talk more about the force on a particle, and that will be in chapter 4, dynamics. Okay. So actually, no, let me talk about that now, and I'll talk about the wave vector later because it breaks the flow. Okay, so this is the yes.
Shouldn't the time component have dW by dt?
Well, no, because I'm writing W to be, I'm defining W where is it? I'm defining W to be dE by dt, right? So maybe a better expression for W would be P for power. Okay. Is that fine? So now let's try and understand some properties of this force vector a little better. So now this is, so far I have been in chapter 2. Now I'm jumping to the beginning of chapter 4. Okay. So let's take the so what are the quantities here? Let us first understand that. Okay. So what is this gamma? This gamma is the velocity of the gamma factor of the particle, right? You have the particle is moving, and at each point, right, it has some forward velocity. The forward velocity has some gamma, which is related to this 3 velocity. That's what this gamma is, all right? So I take the corresponding forward velocity. Now, what is the corresponding forward velocity? It's this gamma VC, comma gamma V vector V. This is the forward velocity. Okay. Now let's take the dot product of these two guys. And what do we get? Well, I get minus gamma V squared dE dt, right? That's this W term. And then plus V dotted with F, vector V dotted with vector F. Okay. Now, what is the vector V dotted with vector F? V is the velocity, 3 velocity, and F is the force vector, the Newtonian force vector. What is this quantity? Do you remember? Anybody? What is the interpretation of this quantity? So let me give you an example. I have an object in circular motion. At each point, it has some velocity, and there is a force acting on this. Now, what is F dot V? Am I still connected? Okay. What is F dot V? In this case, Manikant. Look at this.
0.
0. Right now, does the energy, kinetic energy of the particle change when it's in rotational motion?
No, sir.
No, right? So what is F dot V? F dot V is the rate of change of kinetic energy, the rate of change of energy. Right? Okay. Now, this expression is calculated according to some observer who is looking at the particle. So this is some observer, right? And let's say the trajectory of the particle is like this. And at this point over here, we have some for velocity and some force. Okay, so now, but we can also go to the rest frame. We can ask what are these expressions in the rest frame of the particle. So Manikant, what is the force velocity in the rest frame of the particle?
Set time quantitative basis.
Sorry, I didn't catch that. Can you just repeat? Somebody else? Anand, what is the force velocity in the rest frame of the particle?
Gamma c comma 0.
Right. C comma 0, right?
Yes, sir.
So, and what about the force? The force, similarly, the force 4 vector becomes, gamma becomes 1, and you get this expression. So you get 1 by C, 1 by C, dE by d tau, right? Times whatever the force is on the particle in its own rest frame. Let me write that as F naught. Okay. So if you are in your rest frame and there is some external force acting on you, you will feel that force, right? Just as I explained in the previous class or the one before that, that when you have an acceleration, for instance, even in your own instantaneous frame of rest frame, you will feel that acceleration, right? It won't vanish. Okay. So now if I take the dot product of these two, what do I get? E dot F mu. I get minus dE by d tau. That's it. Because this dotted with this is 0, right? Now what is this E? This E is the total energy of the particle, right? Whichever frame of reference I look at it in. Now in the rest frame, what is the total energy of the particle? Tushar? E is equal to what?
M naught c square.
M naught c square. So in the rest frame of the particle, the dot product of the force velocity of the particle and the force acting on the particle is equal to minus c square d m naught by d tau. And let me the box. Okay. Now, does the rest mass of the particle normally change?
No, sir.
Right? No. So if the rest mass does not change under the influence of the external force, okay, so there is some external force acting on it, Now you could have a force where it affects not only the kinetic energy but also the rest mass. But if the rest mass doesn't change, then what you have this relationship that this is zero, because dm by d tau is zero. So such a force is called a pure force. Okay. And for such a force, we will get another relationship using this expression. So now we can go back to the frame of reference. Going back to the original frame in which the particle is not at rest, right? So in this frame, we have this relationship between V and F, V and dotted F. So this is equal to Vf in the rest frame, right? Because this is a invariant, this scalar product. So this means that if this F is a pure force, then this quantity is zero, right? And if this quantity is zero, that means what we will get is that dE by dt, and there is a minus sign that is missing here, should be a minus sign here, is equal to V dot F, where F is the force and V is the velocity of the particle and E is the total energy of the particle. So again, this is not so surprising because as we already know from classical mechanics, V dot F is the rate of change of the kinetic energy of the particle. But we are talking about relativistic systems. In relativistic systems, this may not necessarily be true. When is it true? It is true when you have this thing called a pure force. Okay. And right. Okay, so I'll leave it here for today. Okay, and now we talked about having the quiz. We'll have the quiz on Thursday, 4th February. Is that okay? Any objections? For the 4th of February. Okay, so I'll take that as a no, like no objections. Okay, all right. So questions?
So can you give an example of force that is not pure?
So, force which is not pure would, so you imagine that like your particle is moving through, let's say that you have a charged particle and it moves through some medium, which is a dielectric medium, let's say. So in that case, so well, not a pure force is anything which causes the rest mass of the particle to increase, right? So the rest, that means that basically the particle is absorbing some energy or releasing some energy in its own rest frame, right? As an example, you can think of a black hole. Black holes are thermal objects, right? So a black hole is evaporating in the rest frame of the black hole. The black hole is evaporating. So one would say that the rate of change of so the question is that you can now look at the black hole from the perspective of an moving observer, right? And you can ask, what is the force for vector acting on the black hole? So you will find that even in the absence of any external force of this form, so you don't have any force which is changing the kinetic energy of the black hole, right? But you will still find that this force for vector is not zero, right? Because of this expression W, which says that the rate of change of energy of the system is non-zero. Okay, and let me see. So that would be one example. So steam refers to such a force as a heat force. So you can think of a system which is either absorbing energy or emitting energy. So it is surrounded by some thermal bath. And in classical mechanics, we would not have that description, right? We would say that, okay, you can have an object in a thermal bath, and that object can absorb photons or emit photons. But in the classical picture, we would not say that that corresponds to an increase in its change in the inertia of the object. We would say that the temperature of the object varies, but we wouldn't associate that with a change in the inertia of the object, right? And force is a measure of inertia, right? So if you have either something which is causing the kinetic energy to change, that's also a force. And if you have something which is changing the inertia of the object, that is also a force. Okay. And I mean, there are probably better examples, but I can't think of any at the moment. Okay. Of course, if you find some examples, you're more than welcome to share them with us. Okay. So, okay. In the next class, what we will do is we will talk about, we'll look at some of the topics which are covered in chapter 3. So one of those will be the Doppler effect, right, which is a very important relativistic effect. And then we'll talk about this aberration and the headlight effect. And then there is one second. Right, and then I will try to talk about this Penrose. There is something called the Penrose effect. It's called the Penrose-Teller effect, and I'll talk about it if I have time. And then there is another very important very important aspect, which is, I forget the name of this effect. It's called something, but it happens in astronomy all the time. Is that when you have these objects which are called quasars, quasi-stellar radio objects, which are basically generally they are galaxies with some black hole in the center, and that black hole is mass is accreting around the black hole, and it's falling into the black hole. Now, as the mass falls into the black hole, all the particles get stripped from the atoms, right? So everything becomes charged. So you have these massive amounts of charged particles flowing around the black hole as they fall in. Now, what that does is that generates magnetic fields, right? Because you have these huge currents flowing in circles, right? So these generate magnetic fields. And then as a consequence of these magnetic fields, right, the same charged particles experience a force in the direction perpendicular to the plane of the galaxy in both directions, right? So the rotation is in this direction, and it generates these helical magnetic fields, and these charged particles are ejected out in both directions, to the left and to the right. And they are ejected at velocities very close to light. So now what happens is that when an observer looks at these jets from a distance and calculates the velocity of the jet, it can appear to that observer, to that external observer, that the jet is moving at a superluminal velocity. So that is an apparent effect. It is not a genuine effect. It's a consequence of so it's a apparent visual. It has to do with the Doppler effect and time dilation and all. So that I will talk about in the next class. I think that's really interesting. Okay. All right. Any questions? Okay. All right. So then I will stop the